Module 7.2 Theoretical Foundations of Machine Learning. In this module, we'll learn about these four key steps, such as data, how to define the problem, how to collect the data, how to visualize the data, how to select an appropriate model, how to train the model, and what does it mean by training a model, and then how to evaluate the model and deploy the model. Now, defining the problem. It's actually very challenging to how to define or determine the problem. So determining the objective is first step for applying machine learning. We should clearly define the problem you want to solve and the goals you want to achieve with machine learning. I know sometimes it could be not that easy, it's not that simple, but it's good to have as much as clear idea as possible. If you understand the problem and understand the specific issue or opportunity that machine learning can address, it will be very useful. Then we can have objectives, clear measures, metrics, and scope of the project. Also, we have to get a hand on what kind of task we want to perform, supervised, unsupervised, reinforcement learning, or a combination. Usually, for a completely unknown task, we go first with unsupervised task, then supervised task, and then reinforcement learning. But that's not always true. Now, we keep emphasizing on data collection and data analysis. Garbage in, garbage out. Always have uh, good and high quality data um, to train and evaluate machine learning model. Identify the data sources. So luckily, we live in a very golden age of data mining or data-driven methodologies. So there are a lot of databases, publicly databases, or you may want to develop your own database for a particular problem and apply the machine learning model. We can collect the data, ensure that it is relevant and sufficient for the problem at hand. Always, there is no clear evidence that this data is sufficient unless you actually train it, the model. So it's kind of a chicken and egg kind of problem. However, we have to start with the data we have. And as we said, we have to store the data in a particular format or it's already available somewhere, such as for atomic structure data sets. We already looked into some of this data set in the previous modules, such as RCSP, Protein Data Bank, Jarvis DFT, Jarvis FF, Materials Project, Open Quantum Material Data Set, Automatic Flow of Library Data Set, Coarse Graining, Phase Field Data Set, and also there are many other general data sets such as Figshare, Zenodo, Kaggle, and of course there are some people can put the data set in GitHub and so on. So always search for a particular data set, a problem that you are working on. I'm pretty sure there should be something relevant out there publicly available. Or you have to generate your own data. Now, once you have this data, first thing we do is have EDA or exploratory data analysis. In that, we perform descriptive statistics to calculate a summary. We'll learn that in the next module, how we visualize the data such as histograms, scatter plots to understand the bounds of the data. Because again, machine learning models are very good for interpolation, not good for extrapolation. So you have to understand the interpolation range, especially for this multidimensional data. Correlation analysis to identify the possible correlation between the features or the data set. Now, once we have the data, now you have to select the algorithm very wisely. Depending on the problem you're trying to solve, you might have classification or regression, linear regression, decision tree, neural network. Usually we have tabular data, such as you have features and we have the target, then usually something like decision trees is very good. If we have data such as images, then convolutional neural network may be very good. If you have data set such as atomic structures, we might be using graph neural network, or if you have text data, we might be using transformer for text and so on. Or it's not always super obvious. You might use a combination of this model as well. You always have to benchmark the model accuracy and performance. And for this, establish the evaluation criteria, such as a mean absolute error versus R square, or accuracy of that model is very important. After that, we have to select a model. There are gazillions of models available out there. So um, for a particular problem we try to solve, you might use all of them, or you can wisely choose one of them or a couple of them based on the literature uh, resources. Now let's go over some of the tour of machine learning models. There could be dimensionally reduction models where we want to have where we have multiple features or inputs, and then we instead of using, for example, 1,000 inputs, we want to use two inputs. So how to crunch that thousand input information to two input or two dimension is what is dimensionally reduction, and it can be used PCA or tsne or UMAP or so on. We'll try to use some of that in our hands-on tutorial. Of course, we cannot use all of them, so keep in mind that we'll be discussing only a few of them, but there are resources out there, and also I'll point out to you, you might be able to learn more if you want to learn more. Instance-based methods, so compare instances in data with similarity measure to identify best matches. Regression models, so establish relationship between independent variable x, that is input, and output variable y uh, to optimize the errors made in predictions, such as logistic regression, neural network, and decision trees. These are some of the models. Clustering model describe the class of the problem, defined different from the classification. It works with unlabeled data. Regularization models, which penalizes the model based on the complexity. We talked about the complexity in the previous module. Bayesian algorithm. The good thing is about Bayes algorithm, it can give uncertainty in the predictions, so such as the Bayesian network. Ensemble models, where models are composed of multiple weaker models that are independently trained and whose predictions are combined in some way to make the overall predictions better, such as a random forest, gradient boosted regression, AdaBoost, and so on. We'll also learn that using the hands-on session. And of course, very popular neural network algorithms, which are inspired by the structure and function of biological networks in brain. And some of them are multi-layer perceptron, convolutional neural network, graph neural network, transformers, autoencoder, and diffusion model. We'll only deal with some of them in this particular module and exercises. Now let's go over some of these models briefly. So linear regression, as you can see, we are trying to establish a relationship between y and x in a linear way, which has a slope and intercept. So y is a dependent variable, x is a independent variable, beta 0 is, for example, a y-intercept, b1 is a slope. So you can if you have multiple data set, you can try to uh, get the value of beta 1 and beta 1 or theta 1 and theta 2 in the above equation to make a future predictions for arbitrary x. So that is the idea of linear regression. If you have multiple, also, if you want to optimize this beta 0 and beta 1, you first get the sum of the square residual error called RSS, and then optimize this beta 0, beta 1 so that the residual error is minimal. Now that's the case for one output. You can have multiple input x1, x2, up to xp, and then there also linear regression can be used. Logistic regression, on the other hand, it works with um, logistic function, of course. So here, log odds of an event are considered as a linear combination of one or more independent variable, and is used for predicting binary or category dependent data or variables such as 0 and 1, or true or false, and so on. So logistic regressions, if you see the logistic function, it's just like that. Now, another model, very popular model, is tree-based model. So there we have if and else statement. So for example, age of a person more than 40 or less than 40. How much money is spent, more than $5, less than $5, has kids or not, and so on. So this is based on this decision, we can make a tree and if then rule to generate predictions from one or more decision trees, such as random forest and gradient boosting. And there we use the idea of Gini impurity, where Gini, where pi, it uses the pi as a proportion of sample belonging to a class I in the node, and from there you calculate the entropy, and there are several tools that are underlying the tree-based algorithm to make a reasonable model. Now, more powerful model are standard neural networks. So here, for example, if we have X1 and X2 as input, suppose this is aluminum and nickel, and you want to combine them and you want to see what is their bulk modulus, you can always use bulk experiments, or you can use DFT or MD, or you can have a hidden layer or deep neural network to establish a relationship between the output and the input. So it consists of the following parts. First is forward propagation. So first you have to distinguish between X1, X2. So for example, nickel and aluminum can be distinguished between their atomic number or their melting point or so on. So that's called X, or features or descriptors. That descriptors, um, let's call it A0 or X, and then we take that and multiply with a, a learnable weight parameter W for that particular layer, and add a bias term called B. Now that is for layer L equals to 0. You can have multiple layers, L1, L2, L3, and that Z, once we get, we apply a nonlinear activation function, sigma, to get the nonlinearity in the model. And once we have that, we can get Y tilde, which is the output. And suppose Y is the ground truth value, then you can calculate the cost or the difference in the values. And we'll try to minimize this cost by optimizing the weights and biases term using something called backpropagation, using the chain rule, because luckily this neural network models are highly differentiable. So you can get this derivative for very fast. And you keep doing it until your error has been minimized. Now, as you can see, these models, everything is connected to everything. So all the nodes, for example, are connected here. But sometimes if you have, for example, images, then you have huge number of parameters in that model if you connect everything to everything. The idea is if you have a convolution filter where you take a block of the cells or pixels and do a convolution, mathematical convolution operator, and then after that you make a convolve feature, and from there you perform a standard neural network. You can have this either max pooling, mean pooling, or sum pooling. So you can take a block and take the maximum value, that's max pooling, or you can have average pooling, take an average of that block, and so on. And then of course do a fully connected neural network at the end to perform a convolutional network. Now that is fine for image-based data, but if you have something like atomic structure or finite element mesh or so on, then the data set is not exactly on a grid. It can be in a very non-Euclidean space. So there we need graph neural network. And graph neural network idea is a graph is made of nodes and edges, or vertices and edges. Now you can define the vertices such as 1, 2, 3, 4, whatever, as a nodes, and you can distinguish them based on, for example, if they're atoms, you can distinguish them based on their atomic numbers and so on, or melting point of that particular element. And you can have to also not just distinguish their chemistry or node features, but also the edge features. So to distinguish edge features, you can see one is connected to 2, one is not connected to 3, one is connected to 5, and so on. You build a matrix where one is connected to 1, one is whenever there is a connection, you put 1, and when there is no connection, you put 0. And this way, you build something called adjacency matrix. And to make it mathematically stable, you calculate the degree of the node, which is basically the row-wise sum of that particular matrix, and normalize with that. And in this way, we'll have node features and edge features, and you update the equation locally. You basically take this features and make it an embedding function, and then I will not go in details of, unfortunately, about the embedding functions to make it everything in a constant shape, and then do it multiple times using F, called propagation function, to get next layer representation, and you keep doing it until you get the best model possible. That's graph neural network. There are other models as well, such as autoencoders, diffusion models, and transformers. I'll briefly touch upon them because they are very popular nowadays. But unfortunately, I don't have time to go in details of this. So autoencoder, for example, are used for dimensional reductions, very similar to PCA, principal component analysis. But here we use a neural network instead of some linear model. And the idea is, suppose you have a 256 by 256 image, you can crunch it into 10 dimension, and then again decode it from 10 to 256 by 256. Now, if you have a new 10 size vector, you can have a new image. And that is how you can make fake images or segmented images and so on. Another idea is, so here we took the image, crunch it to a small dimension, and we learned this process. Similarly, from we learned how to take this small dimension space and expand it. And if we learn this process accurately enough, we can have a generative model for images. However, there are many other sophisticated models, such as diffusion models, where we take an image, constantly add noises until it becomes completely noise, and that from completely noise, we learn how to make complete image model. And this process of reverse diffusion and diffusion can give you a model for a predictive model. Another model is transform model, which is usually applicable for words. So we take all the possible words in dictionary, for example, give them token, such as 1, 2, 3, 4, and whatever, 20,000 or 1 million. And based on that index, we define these three things for query, key, and value pair. So we will try to see how that particular word in that context is related to the other word, and that is defined by something called multi-head attention. And then we also define something called positional encoding. And then we can establish a relationship between one word to next word. And that's how all this autocomplete in your phone or chat GPT or other models works. But unfortunately, we will not go in details of this. Now let's get back to something very simpler, model training. So as we discussed in the previous model, we have to split the data into training and testing, or you can have a validation set as well, training, validation, test. So usually you do 80% training and 20% testing, or you can do 80% training, 10% validation, and rest 10% as validation or testing set. Also, because this training test split can be biased, you want to do it multiple times, like 5 times or 10 times. That is called cross validation. You have to train the model, and then also have to have hyperparameter tuning. We will learn this through the example in the next module. We also have to understand the loss function. So it's not a universal loss function, but one of the most common is the gradient descent. So gradient descent is a fundamental optimization algorithm used for minimizing the cost function or the loss function in a machine learning or deep learning model. So there are different types of gradient descent. Batch gradient descent, where the cost function is computed using the entire training set. So you take the entire training set and calculate the gradient, or you can take a small portion of it or a small batch randomly selected, that is called mini batch, or you can do stochastic or randomly selecting each of the sample and calculating the error or the loss function, that is stochastic gradient descent. Gradient descent with momentum, where we calculate the velocity vector in direction of persistent reduction in cost function and use that to update the parameters. We not only have the cost function, but also have the velocity vector. How fast is it changing? They are also like ADA-grad, RMS prop, ADAM, adaptive moment estimation, especially ADAM-W is very popular gradient descent algorithm, which is used for neural network training and so on. However, I just wanted to point out that understanding the loss function is very important, because when you train a machine learning model or any other model, you have to keep an eye, how does your loss function change? If it is changing, it should, if it's a regression test, for example, mean absolute error is going down or not. That kind of things is especially important to keep in mind. Now, once you train the model, you have to evaluate the model, and there are different type of performance matrices, such as classification. We have accuracy, precision, recall. So, for example, for a classification, you can have true positive, true negative, false positive, and false negative. So, an accuracy of the classification model, such as 1 versus 0, or cat versus dog for image data set, can be true positive plus true negative divided by the entire sample. That gives the accuracy. But if you have regression model where you have continuous output, you can calculate the coefficient R or R square, mean absolute error, and root mean square error. And we have to keep in mind, always calculate the baseline of a machine learning model. So if there's a classification model, and if there's two categories or two classes, obviously the minimal accuracy is 50%, 1/2. And if you have 3, it's 1/3, and so on. So your model accuracy should be more than at least 1/n. If your machine learning model is not more accurate than the baseline model, there is no point of doing machine learning. That's for classification. Similarly, for regression, what we do, suppose we have 80% training and 20% testing. Now, what we can do is take the 80% data, compute the average of the data, such as the Young modulus of all the materials in the training data set, use that average model, average value as a test set value for all the samples in the test set. So suppose it's 5, we will use that 5 as average for all the samples in the test data set and calculate the error. That's called mean absolute deviation. So, or also it's called average guessing model or baseline model for a regression model. So if you train a model and get a mean absolute error, you should always perform better than the mean absolute deviation because a random guessing model. If it's not more than 1, there is no point of again doing machine learning. Always compare and benchmark your results with existing models, of course. Now, finally, once you develop the model, we have to deploy it. Unless you do not want to share it, usually these machine learning models are deployed using a web service such as the Flask, Django, Fast API, Streamlit. We're not going details of these kind of things in this particular course, but just want to make you familiar, such as Instagram was developed with Django. And then once you develop this module, you can host it on cloud-based software such as Amazon Web Service, Azure, Google Cloud, and so on. Also, because dependencies of the modules and tools and data can be continuously updated, we have to perform certain continuous integration, continuous development for platform using PyTest, code coverage, and so on to make sure our code is healthy over time. And we can also submit something called cron job, which can automatically test our whole platform to keep an eye the model is being developed continuously. So these are some of the things for developers, but for our hands-on session, we'll be focusing only on developing some machine learning models, how to compare them, different types of models, what are the hyperparameters, how to get a data set, and so on.